First part of chapter 7.6 is solving exponential equations. An exponential equation is an equation that has the variable in the exponent. So this b of x and the b of y. The foundational statement for today is going to be b of x equals b of y if, or I'm sorry, b to the x power equals b to the y power if and only if x equals y. So if you have the same base and you know that the two amounts are equivalent, then the two exponents must be equal. All right? So if you have an equation such as this, 3 to the x power equals 1/9 raised to the x plus 3 power, if you had the same base, you would know that your exponents are the same. And so the trick with this is simply going to be to finagle the numbers such that those bases are the same. And if you look, 3 and 9 do have a factor of 3 in common. And so if you had this 9, if you change this 9 to a 3 squared, then you do have the same base, except that now it's below. So if you've got 1/9 equals 1/3 squared, now remember, you can put that up into the numerator if you change your exponent to a negative number. So 1/3 squared is the same as 3 to the negative 2 power, right? So 3 to the negative 2 power is the same as 1/9. So we can replace this 1/9 with 3 to the negative 2 power. So 3 to the x power equals 3 to the negative 2 power raised to the x plus 3 power. So far, so good? All right. So now the only trick is we need to get rid of these parentheses so that we just have the base. But that we can do because a power raised to a power, remember, we just multiply those powers. So 3 to the x power equals 3 to the negative 2 times x plus 3, right? And now your bases are the same. If your bases are the same, your exponents have to be the same. So let's ignore the bases for now and say x equals negative 2 times x plus 3. Now this is an extremely simple equation that you know how to solve. So x equals, take your 2 all the way through, negative 2x minus 6. Add 2x to both sides. So 3x equals negative 6. Divide both sides by 3. So x equals negative 2, and you're done. Easy sneezy. All right? Now, that's fine and dandy, but what happens if, say in this one, 9 and 35 don't have a base in common? There's no way to, because 35 is 5 times 7. There are no 3's in that. So what we can do is this. Remember, we can do anything we want to an equation as long as we do the same thing to both sides. So we can manipulate those numbers to make them be what we want them to be. So what we can do is we can take the log base 9 of 9 to the x power. And if we do that, my goodness, this marker, let's switch to green. Can you do that? All right. Log base 9 of 9 to the x power is simply going to be x, right? Because these bases are the same, so this is what this equals. So that's fine and dandy. What did we do on this side? Well, we took the log base 9 of what we had. So we've got to take the log base 9 of 35 now, which we can do. So x equals log base 9 of 35. So now all we have to do is determine what log base 9 of 35 is. And we've already decided that our calculators don't have base 9 in them. But that's okay, because we know how to use the change of base formula. Remember that? Do you remember the change of base formula? So what that says is the log of 35 divided by the log of your base is the same as log base 9 of 35. And you can plug that into your calculator. So if you have a scientific calculator, you just say log 35 divided by log 9 and get your answer. If you don't have a scientific calculator, remember you put in the 35 and then press the log button, and then divided by, press the 9 key and press the log button. And that will give you, what will it give you? That is roughly equal to 1.62. So remember, you're going to have to round it. If you round it to 2 place values, 2 or 3 place values, that's sufficient. All right? So if you can get the same base, and then set your exponents equal to each other. If you cannot get the same base, then take the log of both sides using your base as, using the base of your exponent as the base of your log. And that will free up your exponent. All right? One last thing, because you know I would like to do a word problem. Let's put it into real life. Why on earth would we ever need to solve a problem like this? So, Newton's law of cooling is represented by this incredibly crazy long equation where T sub 0 is the initial temperature. Usually when we have the sub-zero, that's what that means, is the initial of whatever. It's where we started. So that's the initial temperature of whatever it is that we're talking about. And the T base R is the surrounding temperature. So if you've got something that's cooling off, the temperature of the room, or what surrounds it, is that T base R. And then T is the temperature after, so what we're finding, this T, what we're finding is the temperature after this T, there's a lot of T's going on, after the time in minutes. So the time measured in minutes. And then this R is the cooling rate. So having all of that, let's read the problem and then I'll move it so that we can see the equation. So we've got some hot chocolate that we've heated to 90 degrees centigrade, and then we poured that into a mug that is at room temperature of 20 degrees centigrade. If the rate of cooling is 0.145, how long will it take for the hot chocolate to cool to 30 degrees Celsius? So let's use these numbers, and all we're going to do is, once we have the pieces, we're just going to plug them in and then solve. So let's see if I can hold this maybe here. Let's try it. I don't know. All right, so we want to know how long it'll take to cool. So the time is going to be our unknown. Okay, so let's see if we've got all the other pieces. Do we have the temperature after it's cooled off? And we say how long for it to cool, how long will it take to cool to 30 degrees? So that's our first T, is the 30 degrees. So we're going to put the 30 here. 30 equals the initial temperature is where it started. So we cooled, or we heated it up to 90 degrees, and so that's where it starts before it starts cooling. So we're going to have 90 minus the surrounding temperature. Well, we said that it's at room temperature of 20 degrees, so there's the 20 there. And then that is going to be multiplied by e to the negative r, the rate. Oh, they say r equals 0.145. 0.145. T is the part we don't know, so we leave it T, plus we said the surrounding temperature was 20. So 20 goes here. All right, once we've got the parts, I don't have to hold this board anymore. Phew. So now, once you plugged in all the parts, now we only have one unknown. Remember, E is a constant, so we only have one unknown, so we can just solve it. So let's start with the easy parts. 90 minus 20 is 70, so 30 equals 70 E times negative 0.145T plus 20. So we're trying to isolate this part, so let's subtract 20. So 10 equals 70E, negative 0.145T. And now we're going to divide by the 70 to get this part by itself. We're isolating, we're getting it closer and closer to just the variable that we want. So divide both sides by 70. So 1/7. I'm going to see, did I leave it as a fraction? No, I did not. So 1/7, if you take 1, so these are going to cancel. 1 divided by 7 in your calculator, that's going to be 0.143 equals e to the negative 0.145t. All right, so now this is one of those types where, well, we've got this 1.43 base and we have an e base. How on earth do you, what do you multiply to get e? Oh my goodness. So here's the deal. Do you remember that the natural log is a log with base e? So if we take the natural log of e to the negative 0.145t and take the natural log of 0.143, now we've done the same thing to both sides. We took the natural log of both, and the natural log of e to the e leaves us with just the exponent, which is what we want to isolate. We're trying to get this t by itself. And so then all you do is put this 0.143 log into your calculator. If you've got scientific calculator, again, press the log button first. The natural log of 0.143. If you don't have a scientific calculator, press in 0.143 and then push that ln, the natural log number. And that amount is negative 1.94. Go ahead and do it on your calculator and make sure you get the same number. And then you're just getting t by itself, so you just divide by negative 0.145, divide by negative 0.145, and so t equals about 13. So your time is about 13 minutes, and this is rounded to the nearest minute. All right, so the trick is simply with this type, you're going to just put in all the parts and pieces that you know, and you know how to do that, and then do the easy part first. Get all of the extra things, undo them until you get just to your exponential part of your equation, and then you're either going to get the same base so that you can set your exponents equal, or take a log of both sides so that you are left with just the exponent part. All right? You can do this. See you next time.